Good morning, Afton. How is everybody on this fine day? So we got a lot to cover, so I want to go ahead and kind of dive right into it. We'll be talking about imaginary and complex numbers. So let's kind of start off with just this question right here. So when we say the square root of 4, what we're really saying is what number times itself gets us 4? And the answer to that is 2. I mean, 2 times itself gets us to that 4. When we say the square root of 7, we're saying what number times itself gets us the square root of 7. Well, there's no good tangible way to identify that number. There is theoretically some number, some really long number, we call it irrational, that will get us that square root of 7. So when that's the case, what we simply do is we just leave it as the square root of 7. Because there is some number that would get us there. There is some number, again, it would be 2 point blah, 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 blah. Again, really long. But now we look at this. What number times itself, the square root of -1, what number times itself gets us -1? Well, here's where we run into a problem. Because if we think about any number, if we say 1, well, 1 times 1, that gets us 1. So that's out. Okay. Well, then let's think about negatives. -1 times -1 is, oh, wait, it's also 1. Even a negative times a negative gives us a positive. There's no good number in all of reality that can give us this. So what we need to do is we need to go out of the system of tangible numbers that we can think about, of the real numbers that we can think about here. And we will say the square root of -1 equals I, the imaginary unit. That's the big thing that we need to understand, is that when I say the square root of -1, that is an I. That is simply an imaginary number. There is no real number in existence that this can represent. Now you might be thinking, well, Mr. Keith, why? Why would we care about numbers that don't really exist? Well, here's the problem, is that at a certain point, imagination becomes reality. And we'll see that moving forward today. Now, in practicality, let's go ahead and let's talk about this. I have some examples right here. So when I say the square root of -4, well, what we can do is we can think about this as 2 separate problems. We can think about this as the square root of 4 times the square root of -1. We can break that idea apart. And we can say, well, I know what the square root of 4 is. The square root of 4 is simply 2. And we just talked about what the square root of -1 is. The square root of -1 is I. So the square root of -4 is simply 2I. Now, this is what's going on. This is what's really happening here in this problem, is I'm pulling this apart to get to that square root of -1. I never need to see this step. If you look at that and go, oh, it's the square root of a negative, I know that that's going to be I. Oh, it's the square root of 4. I know it's a 2, so it's 2I. I completely agree with you and say, yep, that makes perfect sense. You can move on. So let's talk about the square root of -7. Again, if I think about that, the square root of -1 times the square root of 7. Well, we know the square root of -1 is I, and the square root of 7 is simply the square root of 7. That's it. That's as far as we can simplify it. We can at least say I square root of 7, but that's as far as we can take it. Now, as an aside, here's what I want to point out. I'm sure some of you guys are going to be like, well, Mr. Keith, could we write it this way? Could I write the square root of 7I? The answer is yes, you can write it this way, but we need to be careful. Because sometimes we get a little lazy. Sometimes this square root line starts to extend a little bit, and then next thing you know, that I looks like it's inside the square root. That's a problem. Okay, the I is not inside the square root. When we made an I from this square root of -1, is no longer, it's its own radical, it's its own thing. So don't accidentally make it look like it's back inside that square root. That's a whole different problem. The square root of I Very different problem. So we're not going to get into all that, but just that's the one thing. That's why typically we like to write the I in front of the square root if there's still a square root, just so that way we don't accidentally think it's inside. All right, so looking at this right here, I have, again, I'm going to say the square root of -1 times the square root of 18. So the square root of -1 we know is I. We can break down the square root of 18. We can simplify that, cake method, factor tree, whatever, and we can write this as 3I square root of 2. Now, this is kind of the, if you will, proper format. Again, I don't know if that's necessarily the word I want here, but this is the format that most mathematicians will use. We'll put the coefficient there, we'll put the I there, and then we'll put that square root of 2. But again, if you were to write this, if you were to write I 3 square root of 2, great. I have no problems with that. If you want to put the I in front, if you want to put the I at the end and you said 3 square root of 2I, that's fine as long as that I doesn't look like it's inside the square root. That's the only thing that I just try to stress to you guys, is just make sure. Now, when you're doing these problems on Math Excel, don't just type the letter I. I don't think that works. Down in the bottom, there is an I unit. Make sure that you're using that. Just I don't think Math Excel knows the difference between that I and the I. Again, I'm just trying to help you guys out. So, since we're talking about square roots, we do need to talk about other types of roots here. So it's now we're talking about a cubed root. So we're saying what number times itself times itself. I should have started off with, I mean, we talked about this a little bit. When I say the cubed root of 8, that's simply 2, because that's 2 times 2 times 2 gets us to 8. We talked a little bit about those back at the beginning. So now when I say what number times itself would get us -1. Here's the thing is that, well, if I take -1 times -1 times -1, that is going to be a -1. So this right here is simply our answer of -1. If I were to say the cubed root, if I put these two things together, of -8, that's just simply going to be -2. Because -2 times -2 times -2 would give us -8. The only time that we have an issue with negatives is when the root is even. If we were talking about a square root, a fourth root, a sixth root, and so on from there, that's when there's a problem with negatives. When we're talking about an odd root, they have no problems with negatives. Now, we could talk about the fourth root of -1, but that gets into like this weird complex situation and all that, and then I kind of changes. So we're not gonna worry about that too much. We're only gonna worry about square roots, and then I just wanted to point out, hey, like any odd root, 3, 5, 7, etc., no issues when it comes to that. So that's just something worth pointing out. All right, so let's talk about I as it is I. So I is I. Okay, easy enough. I is I. Now, when we say I squared, let's think about what we're really saying. We're saying the square root of -1 squared. Well, if I have a square and a square root, effectively they cancel each other out. And then I'm simply left with -1, a real number. That's the thing. As I said, sure, we start in this idea of imaginary numbers. But if we end up with enough imaginary numbers and we're multiplying them together, we can end up back in the world of reality. That's why imaginary numbers are important to us. Not because, again, they're this crazy mathematical concept that we're like, well, we're just making this hard on high school students in the year 2020. Like, no, that's not why we have imaginary numbers. The reason we have imaginary numbers is because they have a possibility of becoming real at some point. Just imagine if Santa Claus and the Easter Bunny got together, these two things might be imaginary, but that baby would be real. Again, weird concept, but that's the way that this works. So if I have I to the third, we can use some of our properties. We can use some of our exponential properties here, break this apart, and say I squared and I. Well, we just said I squared was -1. We just said I is I. So then I to the third, or I cubed, is simply -I. We can lose the exponent. Now if I say I to the fourth, that's simply I squared times I squared. So that's just simply -1 times -1. Well, -1 times -1 is +1. Look at that. I to the fourth just gets us a +1. That's pretty cool. Now, I was showing all this work here. I just want to go ahead and kind of summarize that over here. So I is I squared is -1, I to the third is -I, and I to the fourth is 1. So again, just a little summary there of what we just wrote right there. Now let's look at I to the fifth. Well, I to the fifth, I can break apart into an I to the fourth and, not equal, sorry, an I to the fourth and an I. Well, we just had I to the fourth was 1, so really this is 1 times I, which is simply just I. And what we can do is we can keep pulling out these I to the fourth. So this is I to the fourth times I squared, I to the fourth times I to the third, I to the fourth times I to the fourth, I to the fourth times I to the fourth times I. So then with I to the sixth, that would just simply be the same as I squared, which is simply -1. I to the seventh would be the same as I to the third, which was -I. And then I to the eighth is really the same as I to the fourth, which we already know is 1. I to the ninth is the same as simply I. And we can keep going in this fashion. This is what we call a cyclical pattern, is that because of the nature of I, because of the way that this works, no matter what exponent I use, it's always going to boil down to these things right here. So if I were to say I to the 100th, if I were to say I to the 100th, then what that means is that I would just have I to the fourth 25 times. There'd be 25 of those guys there. And then it's a bunch of ones. Well, 1 times 1 times 1 times 1 is just simply 1. We can simplify any I to any power if we just know this fact right here. Now, I'm breaking this down. How did I know that there was 25? Well, I just took 100. I just took 100 and divided by 4. That's how I knew that there was 25. So because this repeats every 4, we can take that exact same idea to this right here. If I have I to the 234th power, then I can simply go ahead and say, okay, well, if I take that 234 and I divide by 4. Now, I know that this is long division. Some of you guys are going to be like, what the hell, Mr. Keith? Go look up some long division. So 4 goes into 23, 5 times, that's a 20, that's 34. 4 goes into 34, that's 8 times. Now, here's the thing. I don't actually care about that number. What I care about is the remainder. I care about what's left over. Because, sure, I would have I to the fourth 58 times. So cool, I'd have 58 ones. Who cares? I care about that last thing. That last thing would simply be I to the second. So that tells me that this is the same as I to the second. They're exactly the same. They just have a bunch of I to the fourths first. So in that case, we can just simply go ahead and we know that this is simply -1. That's it. So if I look at the same thing here, 3,440, I'm always going to divide by 4 because it repeats 4 times. So I take that in there. That is an 8. 32, that's a 2, 24, that's a 6, 24, that's a 0, so this is a 0. So there would be I to the fourth 864 times with no remainder. Now, you can look at this two ways. You can either think, okay, well, which I to the fourth, that's a 1, or you can think I to the 0 power. Well, what's anything to the 0 power, including I, is simply 1. Now, I wouldn't necessarily, again, that's just pointing out that it still holds true even if you think about your properties. But I would just realize, hey, if there's no remainder, this is what I'd ultimately say. If there's no remainder, then we know that it's just that I to the whatever power simplifies to 1. If I look at this guy right here, I can do the same thing. I get 1, 2, 3, 4, 7. Now that's a lot. That's a lot of stuff to look at. I'm going to teach you a trick about the divisibility of 4. I don't actually care about anything beyond the first 2. All I have to do is look at that number right there. That's literally it. I have to do 4 into 47. This is going to be just as good. This is going to get me the exact same remainder. It's a trick. I'm teaching you a trick. Enjoy. So 4 goes in, 1. I get 4, subtract, there's a 7. That goes in 1 time, subtract 4, 3. Because the only thing I actually care about, the only thing is this remainder. Again, I don't care what number that was up there. I only care about that remainder of 3. So I know that this is the same as I to the third. Then I just need to think to myself, well, I to the third, that's simply a negative I. That's it. That's the idea. Now, that's the only new thing that we have today. That's the only new idea that is going on here. All right, this lesson might get a little long, but I'm going to tell you right now that it's just because I'm reiterating a lot of things you already knew. We have to make sure, remember, that we know that I is a square root. So all the things that we've talked about in terms of square roots still hold true here. So if we remember all of the things that we've already talked about when it comes to square roots, then we're fine. Now, let's talk about complex numbers. A complex number is not really that complex. A complex number is a number that consists of a real part and an imaginary part. So if I were to say 7 plus 4i, that's a complex number. If I were to say 6i, is 6i a complex number? Really, it is. Because I could always say 0 plus 6i. Now, it wasn't written in that complex number format, but really, I could write it as a complex number. What about 5? Is 5 a complex number? Now, we don't often think of it this way, but really it is, because I could say 5 plus 0i. Now, again, would we ever write this out in the real world? No, we'd never write a complex number in this fashion. We'd never say 5 plus 0i. But this is what I want to point out, that any number can be expressed as a complex number. Now, with that, we can go ahead and we can perform the same operations, the same everything else that we did with any other number. Now, again, we see this I. You can think about it the same as x, but more importantly, you can think about it the same as a square root, because it is a square root. I is just a placeholder for the square root of -1, so we don't have to just keep writing square root of -1, square root of -1, square root of -1. I is just a placeholder for that. So if I'm adding together two complex numbers, these parentheses are basically useless. They're just to separate, here's one complex number, here's another complex number. Outside of that, they literally mean nothing. Combine your like terms. Well, I got a 4 and I got a 7. That's 11. I got a 3i, I got a -2i. Well, that right there is going to be plus I. Now, you could write a 1I. Again, it's just like, do we write 1x? Do we say a $1? No. But that's it. That's my answer. Now, here might be a little more complicated, but the same way that we can distribute and all that other good stuff, I can still distribute here. So I can distribute this 3 to get 6 plus 15I, and then distribute that minus sign. So we have minus 9, and then plus, why did I write 9I? Sorry, 3I. Looked at the wrong thing. Then again, combine some like terms, 6 minus 9, negative 3, 15I, 3I, plus 18I. Tough? No. Just building on things that we've already discussed. Now they're next to each other. That means multiplying. Yeah, we're going to multiply. Now, unfortunately, when we're talking about a complex number, 2 times 3 is easy. 2 plus 3I times 1 plus I, not that it's hard, it's just not as easy as 2 times 3. What am I going to have to do here? If you said FOIL, correct. So I need to FOIL this out. 2 times 1 gives me 2. 2 times I gives me plus 2I. 3I times 1 gives me plus 3I. 3I times I gives me plus 3I squared. Well, now here's where the trick begins. Not tricky, just things to remember. Have an I squared. We just talked about what is I squared? Oh, that's negative 1. So really I have 3 times negative 1 here. 3 times negative 1 means that I'm going to have 2 plus 2I plus 3I minus 3. Now, I wrote all that out for the sake of writing it out. You don't have to write this out. If you just write negative 3 there, just remember, okay, now this at the end is simply a minus 3. So I can go ahead and I can take 2 minus 3 to get negative 1 plus 5I. The only thing new here is what we just learned about that I squared. Foiling, we've done that. Combining like terms, we've done that. The only thing that's new here is this idea of I squared. And as long as you understand that I would say, all those are important. I'm not going to say they're not important, but honestly, understanding I is the square, I is I, and it's the square root of negative 1, and then understanding that I squared is negative 1, those two are just more important. So I want you guys to go ahead and try that one at your desks. By desks, I mean kitchen table, bed, floor, patio, whatever the case is. Hopefully you paused. Let's go ahead and let's take a look at this. So I'm going to FOIL. So that's going to be 20, and then minus 12I minus 10I plus 6I squared. So again, this is negative 1. So that means I'm going to have a negative 6 right here. So 20 minus 6 gets me 14 minus 22I. Ta-da. Nothing new, just different. Oh man, what do I do here? We FOIL it still. Make sure. Now, on the test, I will say this from the, I believe it's chapter 1. I don't think I saw anyone not do this, which was awesome. That was awesome. I just want to repeat ourselves here. It doesn't change just because there's an I. I still need to write 3 plus 2I times 3 plus 2i. Make sure that you recognize you still need to FOIL by I. So that way on the top here, I'll have 8i. On the bottom, I'll have I squared. Oh, we just talked about what I squared is. I squared is simply -1. And then A, I can just divide that. I don't have to leave that as a fraction. You could, but it's weird to divide by -1 when we can just say -8i. Did you guys know 8 divided by I is simply -8i? Exactly. That's why we do it. Because we want to make sure that we understand. So, questions? Moving on. Now, this problem, I bring up this problem because there are 2 ways to tackle this problem, and no one way is right or wrong. It's just they're just different ways to tackle it. So, I understand that we see that 2i and we're like, okay, I know I got to multiply by what I see down there. So you just multiply top and bottom by 2i. And that's fine if you do that. This is perfectly fine. You're going to end up with 10i, not squared, sorry, 10i over 4i squared. Well, 4i squared is simply going to be -4 with 10i still on the top. And then, hey, I can reduce that. I can't fully simplify, but I can at least make that fraction look nicer and say -5i over 2. So again, not bad, not bad. What you could have also done was you could have just taken 5 over 2i times I. The square root is the problem. The 2 is not. So if we multiply top and bottom by I, then we'll just end up with 5i over 2i squared, which as we just said, that's simply going to be 5i over, that's a -1. So -2. Oh, hey, look, it's the same thing as right there. Again, as long as you're following legal mathematical operations, that's the important thing. As long as you're always doing things that make perfect sense, then it's not a big deal. So let's talk about this. I have 10 over 2 minus I. So now I have that sign. That makes the difference. I can't just multiply by I like I did on the last problem. I can't just multiply by 2i because I have that minus sign there. If I distribute it by a single term, I have to distribute. So that's not going to get rid of this. So I need to multiply by that conjugate. 2 plus I to the top and bottom. And again, as long as it's the same thing on top and bottom, then it's fine. Distribute the 10 on the top, so we get 20 plus 10i over, and then we need to FOIL this out. So when we FOIL that out, we're going to end up with 4 plus 2i minus 2i, and then minus I squared. So notice these things are going to cancel each other out. Awesome. And we know that I squared is -1. So I'm left with 4 minus -1. 4 minus -1, well, that's simply 5. So I have 20 plus 10i over 5. Hey, look, 5 can go into both of those numbers. Since 5 can go into both of them, remember, it has to be both. Since it can go into both of them, we can simply write 4 plus 2i. Look at that. We went from this really odd-looking fraction to a fairly nice-looking complex number. Not bad. All right. One last problem. Double check. Pretty sure. Yep, last problem. So you can try this on your own if you want to pause it, or we can just take a look at it right now. I'm going to take a look at it right now, but you could have still paused. So multiply by the conjugate. 1 plus I to the top and bottom. Remember, I just need to change that sign to get the conjugate. That's the easiest thing to do. So I'm going to have to FOIL on top and bottom here. So when I FOIL on, I just like to FOIL on the bottom because I like to make sure that everything drops out the way that it should. So 1 times 1 is 1. and then that's going to be a plus I minus I, and then minus I squared. Which, yep, cool, that I and that I cancel each other out. I'm left with 1 minus negative 1. So that means I'm simply going to have a 2 as my denominator. So I said I like to always multiply the denominator first, just because that way, if I didn't cancel out the I know, wait, I need to rethink this. So FOIL the top here. Especially, I'd hate to FOIL the top and then realize, oh no, I messed up. So I FOIL the top. I end up with 8 plus 8I plus I, and then plus I squared, which we know I squared, again, is that negative 1. So then I'm going to have 8 minus 1, which is 7. And then 8I and I is 9I. Unfortunately, sure, we got a 2 here. But 2 can't go into either of those numbers, so I'm just kind of stuck. Now, for me, if we were writing answers, I would tell you that this is perfectly acceptable. This is perfectly fine, and there's nothing wrong with it. However, the issue becomes this is not in that A plus BI complex number form. So while this is fine for me, to write it in that proper complex number form, we would need to say 7 over 2 plus 9 over 2 I. Again, this is strictly for that nice A plus BI form. If it was me, great. But I can tell you right now, some of those Math Excel problems, I was like, they're going to make you write it in complex number form. So just remember, you can always separate one big fraction into smaller fractions, as long as there's one number in the denominator. Except for the idea of I. Again, these were all things we've already discussed. We already took time to make sure that we knew how to do them. So this is just adding in a layer to something we already knew. So that's all I got. If you have questions, again, email me. You have an assignment on Math Excel. I believe it is imaginary and complex numbers is the name of it. So on that note, I will bid you adieu. Until next time, stay safe out there, Afton.